Now here are some examples again of Lewis structures of various compounds. And the top two are fairly straightforward. You have a hydrogen with one electron combining with bromine, and you show that with hydrogen bromide with 8 electrons around the bromine and the hydrogen beside it. Similarly with hydrogen sulfide, you have 2 hydrogens that combine, each contributing 1 electron to the shared pair. Now with the third one here, I want to show you, using the rules again, how you end up with, you start out with N and N. Each of these has 5 valence electrons, and you put them together first, and you use a single bond to link them together. So that goes from 10 to 8. And then you put the rest around the outside like this. Now you notice that if you do that, now that's all 8 of them. If you do that, you end up with nothing that you can do anything with here. You have 6 electrons around here, 6 electrons around here. That doesn't fulfill the rule of octet. Okay, and so you'll take one pair and move it in. So you have N and 2 bonds now, N, like that. But you fulfill now the rule of octet. You fulfill for this one. It has 8 electrons because it gets 2 paired. It gets 4 from this, and then 2 pairs there is 8, but this one doesn't get it. So then you take another one and put it in here for sharing, and you end up with what's on the slide, which looks like this. And this represents 6 shared electrons, plus 2 is 8 on this side, plus 2 is 8 on that side. So everybody's happy. So that's what in the rule here that says form double and triple bonds to maximize octet. That's what we're doing here. So let's look at some other examples. We're going to draw the Lewis structures for these four compounds. So you start out looking like this. So you have these 4 compounds, and it will start out looking like this, but I'm going to do it on the drawer here so I can show you everything that we're doing. So you start out, you arrange the atoms around a single central atom. In this case, and in this case, you can do that, but in this one, you really can't. But actually, the first thing you're supposed to do is count your valence electrons. So let's start with Si and hydrogen. You have 4 hydrogens, so there are 4 valence electrons here and 4 with Si, so you have a total of 8. So then you start out with Si in the middle and the hydrogens all around it, like this, and you connect those with each with single bonds, and then with Si you're done because you've used all 8 valence electrons. Each of these represents a pair, so there are 8 around the Si, and the hydrogen doesn't need anything else, so it's happy. You do this. Now remember, with a negative ion you have to add 1, so you have hydrogen, which is 1, you have carbon, which is 4, oxygen, which is 6, and another oxygen, which is 6, and then it has a negative charge, so that's 1 more. So that's a total of 12, 13, 14, 18 valence electrons. Then you draw, as it says, you draw these around like this, and you've chosen this as your central atom, which is, this is common to choose the non-hydrogen single atom as the central atom. So there's 2, 4, 6, so that's 12 left over. Hydrogen doesn't get any, so you can put the rest of the 12 around the outside here, and you can do it like this. And so that's all 12. So this has 8, this has 8, But regrettably, this carbon in the middle doesn't have 8. So it's not happy, okay? And there are things that you can do about that. You can take one of these, and we'll go through the slide here and show this, and move it in here like this. So now you have H, C, single bond, O, 1, 2, 3, 4, 5, 6, double bond, because you've moved one in, O, 1, 2, 3, 4, and now everybody's happy. You've got 8 in the middle here, you've got 8 here, you have 8 here, and you have hydrogen over here. So that's how you do that one. Looking at this one, you get 5 from nitrogen and 6 from oxygen, minus 1 for the plus sign. So let's take that and drop it down to 5. So you end up with 10. So you have N-O. That uses 2, so you're left with 8. And you can use 2 on each of these, like this. But then you're left again with one of these only having, each of these only having 6. So again, you have to think about dropping in one of these guys in the middle here. So you have N dot 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 2 bonds, O dot dot. This one still only has 6. So we could take one from this one. So you have N dot dot, wait, let's put it over here. 3 bonds, O dot dot plus. And there you go. The last one, fluorine has 7. 2 times 7 is, well, let me get a fresh sheet of paper here. 2 times 7 is 14. Plus oxygen, which has 6. So that's a total of 20. You start out with the O in the middle. And then, so that uses up 4. So you have 16 left. And you know you're going to have 6 around the outside of these fluorines. So that's 6 and 6 is 12, which leaves 4. And you can put the remaining those in the middle like that. And that uses the rest of them. And everybody again is happy. 6 plus 2 is 8. 4 plus 2 pairs of 2 is 8. 6 plus 2 is 8. So now let's go through these slides which show you the same thing, stepwise fashion. And this is the kind of thing you'll have to do on a quiz or a test. So you start out, as I said, attaching each of these with a single bond. Then the next step is to distribute the remainder as pairs around terminal atoms. Now, the first one on the left here didn't have any remaining. The second one is what I did where I just put all the remaining 12 around the outside of the oxygen. The problem with that is you're left with the carbon having only 6 instead of 8. Similarly, if you put the remaining 8 electrons around in the way it's shown here, and even if you do it by putting 6 around the oxygen and only 2 with the nitrogen, you're still coming up short. And then lastly, you have this fluorine, each of which has, it's around the terminal atom, so each of these has 6 and 6, but you still have 4 left over. So the next step is to place the remaining electrons in the central atom, and that, as you remember, fixes the one compound that we were working on. And then making multiple bonds to maximize the rule of octet fixes the last 2. And again, this is what I showed you on the paper. You can, and on the top one here, it doesn't have to be the pair that's shown. It could be the other oxygen, a pair from it. As a matter of fact, some people will talk about resonance next week. What happens is sometimes it's a pair from one of the oxygens and sometimes it's a pair from the other one. And that situation is known as resonance, but we won't talk about that right now. Now, I told you that the rule of octet was almost always fulfilled, but I wanted to show you an example where it's not fulfilled. And here's one example. You have an odd number of electrons. This molecule exists. Nitrogen monoxide exists, and there's no way with 11 electrons that you can fulfill the rule of octet in both compounds, in both atoms. And here's an example of electron deficient molecule. Here's a situation where you have the beryllium combining with, boron trifluoride combining with ammonia to form this compound. And you can see that the boron trifluoride is an electron deficient molecule. But when it combines, you end up with everybody happy and the rule of octet achieved. And then the last example here is an example where you have 5 pairs of electrons around the central phosphorus. So it also breaks the rule of octet. And sulfur hexafluoride has 6 pairs. So there are examples shown here where compounds can again violate the rule of octet, but these are unusual exceptions to the rule that governs well over 99% of the various types of bonds.